Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will do some cases in Pipesim. First, we will do nodal analysis for a horizontal well with multi-layers. And after that, we will install electrical submersible pump to this well. All right, so let's dig in. General, well name, horizontal well, multi-layer. All right, and then it's an active well, of course, well type production, check valve setting, block reverse. Okay, we go to tubulars, we change to detailed mode, dimension option, wall thickness. Okay, so we will have casing, and after that we will have liner. All right, we can call it liner. Okay, so from 0, you can follow me to 6,100. Inner diameter, it's quite big, 8.835, and with wall thickness of 0.395. Okay, and roughness, this one. You can also use the catalog if you want. We can open it. All right. Okay, so this is the catalog. Okay, and for the liner, of course, from 6,050, we will install the liner down to 15,100 feet. All right, so it's a deep well with inner diameter of 6.094 inches and wall thickness of 0.453 with default roughness. All right, so and then we go to the tubing. We can take this tubing and we can drag it down. Okay, we call it tubing 1 from 0 down to 6,000. All right, and wall thickness, I mean inner diameter of 6 or 3.476, wall thickness of 0.262, 0.001 roughness. And for the second tubing, we call it tubing 2. All right, 7,400 foot, and it is smaller, 3.068 inches, wall thickness of 0.216, default roughness. Right, so this is our well configuration. We have casing, we have liner, and we have tubing 1 with bigger size and second tubing. Right, so from here we go to deviation survey. All right, we will have horizontal well, so we go to 2D. Well, head depth at 0 and bottom depth at 15,100 feet. And this table will be quite long. All right, so you can follow me. You can bear it for a while. All right, 0 measured depth, 0 through vertical depth, and after that 500 as well, and after that 1,000. So we still have vertical section here, 1,500, the same. And we will start deviating our well from here, 2,000. All right, we start the deviation, 2,500. Okay, and for the 3,000, yeah, you can feel it, right? You can see it. It turns to horizontal, 3,500. And after that, 4,000, 3,780, and 4,500, 4,163. You can add a little bit more, 5,000, 4,511, okay, and 5,500, 4,819. And we continue, 6,000, 5,076, and after that, yeah, in reality, you can ask your peer, especially drilling engineer or completion engineer, workover or well service engineer. They have this data. Okay, as a software engineer or production engineer, you will create nodal analysis, and for the deviation survey, you get that data from drilling engineer, completion, workover, or well service engineer. Okay, so let's continue. 7,000, 5,426. You can add more. 7,500. Okay, bear with me, guys. Right, 8,000. Okay, it becomes clearer. We have horizontal well here, 8,500. Okay, you can see the angle, right? Calculated angle. We go to 90 degrees. Okay, and then 9,000 feet. We go to 5,687. We add more. Okay, 9,000, 9,500, 5,730, and then 10,000, 5,765. And I hope this is the last interval, maybe. All right, not yet. Okay, we still have more, 11,000. Okay, okay. Now you see we start the pure horizontal section from now on. Okay, the same true vertical depth, right? The same true vertical depth, 12,500, the same. Okay, you can copy the cell and paste on the table. 13,000, 13,500, 14,000. Okay, hopefully this is the last one. And copy, paste, right? You can see the calculated angle, it's 90 degrees. All right, so this is our horizontal well. It's quite easy, but it's quite long, but no problem there. You can also get the table by clicking this icon. All right, view data in table. All right, interesting. Now we go to downhaul equipment and we will install our subsurface safety valve. And we call it SSSV. We put it at this level, 380. And we also have packer, right? You can see our SSSV here, and our packer will be located at 7,300 feet. Okay. All right. And for the SSSV, the bin size, let's say 2.36. All right, the bin size of our valve here. And we can install our artificial lift, but for our first case, we will do natural flow for the nodal analysis. All right, so we can leave it as it is, and we go to heat transfer. Right, so for the heat transfer, you can follow me. We will have multiple, and ambient temperature input also multiple. We will have 12 rows. Okay, 10, 11, and 12. 0. All right, 8,000, 8,500. All right. Okay. All right. We will have constant U values of 2. Okay. This is our constant U value. And for the ambient temperature in Fahrenheit, 50, 160, 161. Okay. Okay. All right. So this is our table, and this should be 2. All right. We have constant U value. We can assume that. And this is the temperature profile, temperature against measured depth. You can also get the table. You can copy and paste on your spreadsheet, right? Okay, so far so good. And now we go to completion, the most important section for the inflow performance relationship. We will have 3 layers. Okay, we can call it upper zone, middle zone, and then the bottom one. Okay, we will have horizontal. Okay, we have 3 reservoirs and 3 PVT data. And the fluid entry, we will go to distributed. Okay, and for this one, the completion or the perforation, 7,500 to 8,500. So although we construct a horizontal well, but in my software, the well sketch is still in vertical shape, but maybe in your software, it turns to horizontal shape. No problem there, because in the calculation, this deviation survey will be used. Okay, go to completion again. For the middle zone, 10,000 to 11,500. And for the bottom one, 13,500 to 15,000. Okay, so as you can see, we have 3 layers, 3 reservoirs. And for the IPR model, to make it a little bit more challenging, for the upper layer, we will use Joshi, steady state. And for the second one, we will use this one, Babu and Ode for pseudo steady state. So as you can see, Joshi is applicable for steady state condition and Babu and Ode for pseudo steady state condition. And for the last one, distributed PI. Okay, the simplest one. All right, so now we go to first layer, Joshi. Okay, you can follow me. The reservoir pressure 1560 with reservoir temperature of this one, IPR basis, of course, liquid, radius of reservoir extent 1100 feet, reservoir thickness of 48 feet, permeability of X perpendicular to the well. Let's assume very homogeneous reservoir. We have the same permeability for X direction and Y direction. Okay, parameter option, we will use absolute. Okay, and for vertical permeability, 20. Okay, and well radius, 8 inches with well eccentricity, 12. Okay, 12 feet. All right, so far so good. From here, we go to skin. All right, for the skin, let's check it first, the reservoir section. Okay, and for the skin, we can use specify or calculate one. We go to calculate. Completion method, we will go to perforated with no gravel pack, and we will use absolute mode. For the damage zone, let's assume 40 millidarcies. Thickness, very short, for only 4 inches. And for perforation, partial penetration, and deviation, we go to first perforation density, 6 shots per foot, and diameter of 0.48. Okay, quite proper for the diameter of the hole, and the length 12 inches, quite deep. Okay, and for the compacted crash zone, permeability should be lower, 20, half of the damage zone permeability, and for the thickness, even thinner, all right? But the impact is huge for the productivity. Okay, so this is for the skin data, all right? And now we go to second one first, and later on we'll install the fluid model. We go to second layer. Okay, this is the data sheet. The reservoir pressure is quite different. In the first layer, we have 1560, whereas for the middle zone, we have 20 psi higher than the first layer, right? So we have different hydraulic system, we have different reservoir indeed, okay? And for the reservoir temperature, 165.91, reservoir X, this one, dim is dimension, okay? Reservoir Y dimension, okay. And reservoir thickness is quite thick. And for the X direction permeability, again, we assume very homogeneous. X and Y the same. By homogeneous, I mean the same permeability in X and Y direction, all right? In vertical direction, we have different permeability value. Okay, that's why for the permeability anisotropy, we will use, or maybe we change to absolute rather than ratio. And for the vertical permeability in Z direction, we only have 14, all right? Far below the X and Y permeability, all right? Which is quite normal. And for the heel location, X, Y, and Z position, you can follow me, all right? So this is for the sake of illustration. In your real case, you need to know the reservoir geometry. You need to maybe create the reservoir model and reservoir simulation first, and maybe geomechanical model before finally you can obtain these numbers, all right? But for the sake of example, we can use this example as an effective or good example for us to exercise. All right, so for the Z position, 69 and well radius of 8 inches. Okay, now we go to skin. You can just specify 1, 2, or 10, right? But yeah, for a little bit more theoretical or analytical, let's do the calculation. Completion method perforated, go to absolute, damage zone, skin by damage, 38, thickness 1.5, and skin due to perforation, partial penetration, and deviation. Perforation density again 6, and diameter of 0.48, and length 12 inches. All right, and for the compacted or crushed zone, 32, permeability, and thickness of 0.26. All right, lastly, we go to the bottom zone. For the distributed PI, it should be much simpler. We have the bottom zone, so yeah, we can say the reservoir pressure will be a bit higher. That's why we have 1600 here. And we have hotter as the temperature. And productivity index, let's say 0.12. Okay. All right, so now let's create the fluid model. Okay, we go to upper zone first. We make the fluid model. Okay, let's call it a fluid with water cut of 0.5. Later on, we will increase the water cut and we will see the nodal analysis results. And GOR, gas oil ratio of 460 standard cubic feet per stock tank barrel. And gas specific gravity, let's say 0.7, water specific gravity of this one. And for the API gravity, 48. All right. This is for the first layer PVT, and for the second one, for the middle zone, we add another PVT fluid model. Okay, we go to B fluid. All right, and then water cut of 0. Or maybe 1.2 with GOR of 430, gas specific gravity of 0.8, and water specific gravity of 1, API gravity of 46. All right, you can modify, okay? You can modify a little bit to see the effect. And we have CO2, 0. Infractions, and nitrogen to make it more, right, spicy. Okay, and then for the bottom zone, fluid model, new. All right, we can call it C fluid. Okay, 2. water cut, GOR of 410, gas specific gravity of this one, water specific gravity of 0.9, and API gravity of 47. All right. And for the CO2 fraction, 0.00 or maybe 115. And for this one, yeah, let's do this. Okay, so as you can see, you see the sign, we are validated. From here, we can perform the nodal analysis. All right, so far so good. Let's see. We go to home, we go to nodal analysis, select location, bottom hole. We as petroleum engineer, reservoir engineer, or production engineer are more interested in the well itself. So let's concentrate ourselves on the bottom hole rather than the wellhead. Okay. All right. So for the outlet pressure, by outlet pressure means wellhead pressure, the head or tubing head pressure. All right. So the outlet pressure is 200 psia with no sensitivity analysis. So we can run and let's see the nodal analysis. All right, so you can see we can flow. All right, we can flow. This is our composite IPR, the blue curve, and the VLP, vertical lift performance, or the outflow, the red curve. You can see the IPR curves by layer by clicking this one. Okay, where is it? Okay, bubble point here, the calculated bubble point. And for the view operating envelope, this one. Okay, I don't know why we cannot show the IPR curve by layer. This is the profile results. Okay, the pressure to the wellhead, from the reservoir to the wellhead. Okay, so as you can see, we can flow, and our flow rate is 6,739 stock tank barrel per day with bottom hole flowing pressure of 1,483 psia. You can also get the numerical value by clicking this one, view data in a table. You can copy and paste on your spreadsheet. All right. We go to the picture. All right. So this is the nodal analysis for a horizontal well with 3 layers, with multi-layer. So we have created nodal analysis. We have constructed a horizontal well with 3 layers, and we perform the nodal analysis, right? But we can go farther. Let's say, what about override phase ratio? Let's say we assume increased water cut. Maybe we are close to an aquifer and we experience significant water cut increase. What will happen to our well? Okay, so as you can see, for initial condition, we have a very low water cut of 0.5, 1.2, and 2. Let's say what happens if the water cut is increased to 25%. So we get more water in this condition. All right, it will make the density of our flowing fluid higher, heavier. Maybe our well will stop flowing. All right, so let's make sure you click this one, override phase ratio, and change the water cut value with 25. Let's see. Right, you can see we still can flow. Okay, so what about increasing the 240 maybe? So our objective is making the well stop flowing, and from that condition we will install artificial lift. So that's our objective for this case. Let's see. Yeah, still we can flow, but as you can see, we go to the maybe to the last limit of our well. As we experience higher and higher water cut, heavier and heavier fluid density, our well will cease flowing. Okay, let's see for water cut of 50, which is not rare, not seldom. Very, very easy. We can find oil with water cut of 50%. Run again. Wow, we can still flow. No, as you can see, unconverged. All right, so at the water cut of 50, our horizontal well cannot flow. All right, now our well ceased flowing. From here, we will install the artificial lift. And because we want to achieve high flow rate, we prefer electrical submersible pump. Okay, hopefully our pump will make our well able to flow again. All right, so that's our agenda. So from here, with this condition, with water cut of 50, we will create our ESP. Close. Now we go to artificial lift and we click this one. Okay, we go to our ESP. We change from PCP to ESP. All right, it's going to be interesting, hopefully. Okay, and then for the ESP, let's call it ESP active. We will locate our ESP at 6,000 feet. Right here, you can see, and we will select the manufacturer. We will go to REDA. So this is our catalog to find our ESP. Okay, so our casing ID is this one. So the catalog will be filtered in such a way that it will only, that it is able to be contained in a well with this size of casing ID. Okay, so for the manufacturer, we go to REDA. Okay, and we will find JN. Okay, JN 10,000. Series 675. All right, so we expect flow rate in this range, 8,250 through or up to 14,500 stock tank barrel per day or barrel per day at operating frequency of this one and clearance this one. Okay, we click OK. All right, so this is our ESP. You can see the size of our ESP, it's quite huge. And this is the pump curve. The blue line is the head. The green one is the power. And the red one is, of course, the efficiency. And the yellow zone indicates the efficient area of operation. And also the range of our flow rate. As you can see, the minimum flow rate is 8,250 around here, and maximum flow rate of 14,500 barrel per day here. And the top of our efficient operation will be located at this one, the peak of the red line. All right. Okay. And for the operating frequencies, 60 hertz. And for the stages, okay, we only need 25 or maybe 28. Okay. This is the calculated operating speed and had the rating factor 1 and rate the rating factor also 1, power the rating factor then will be 1. And this is the variable speed curve. This is the performance curve. As usual, you can obtain the value by clicking this one for the performance curve and for the variable speed curve. Okay, and for the calculation options, stage by stage calculation. Okay, and let's also check for the viscosity correction. All right, again, we are validated. We can now perform nodal analysis after the well has been equipped with artificial lift electrical submersible pump. Let's hope for the best that the well now is able to flow again at this condition. All right, so we click run. All right, as you can see, now after being equipped with artificial lift with electrical submersible pump, now we can flow with flow rate of this one, 8,500 stock tank barrel per day at bottom hole flowing pressure of around 1,470 psia. All right, so it's beautiful. Again, bubble point, operating envelope, okay, and obtaining data in table. And again, we can see the profile results, right? The pressure increase is quite clear. You can see the pressure at reservoir zone is around 1600, 1600 psia, and then it will go down. All right. And after that, it will find the ESP, right? The ESP, and by the ESP, the pressure is pumped, is increased significantly from here around 1250 and then go up to maybe 1800 psia. And from that, we go to wellhead pressure of 200. All right, so this is the pressure profile. And again, this is the nodal analysis. All right, so yeah, we can also do sensitivity analysis. Like for the ESP, for the outflow sensitivity, we can increase the frequency. And let's say we will use 3 frequency numbers, 0 if we assume that the well doesn't have ESP. So we assume we make it similar with ESP but 0 frequency, and 60 the base case, and for the optimum case 70 hertz. What will happen? All right, again, as you can see, with 0 frequency, we cannot flow, right? With frequency of 60 hertz, we can obtain stock tank barrel per day of around 8,500 stock tank barrel per day. And if we increase the frequency from 60 hertz to 70 hertz, we can increase the flow rate up to 10,250 stock tank barrel per day. All right. Whereas the bottom hole flowing pressure only decrease only 8 psia, right? For the 60 hertz frequency, the bottom hole flowing pressure is 1,468, whereas for the frequency of 70 hertz, we have bottom hole flowing pressure of 1460 or 61 PSIA. And this is the nodal analysis. All right, I think that's all. So in this case, in this video, we have created a horizontal well with multi-layer. It's an oil well, and we perform nodal analysis for natural flow case, and we increase the water cut to mimic a natural water cut increase for whatever reason, right? And we can see that from nodal analysis, the well will cease flowing at water cut of 50. And from that, we install artificial lift, we install ESP to make the well able to flow again. All right. And we also do sensitivity analysis by changing or by making three scenarios of frequency: 0 hertz to mimic a natural flow well, and 60 hertz as a base case, and 70 hertz as an optimum case. All right, so that's all. I hope you enjoyed the video. I hope the video is useful, and please subscribe, like, share, or comment to your friends, or comment to the channel, of course, and see you again in the next Pipesim videos. Thank you.